Hi everybody, this is Dr. Bricker here with some hints for homework 4. Homework 4. So here's the first question. The current through the 30 ohm resistor is 0.5 amps. What is the EMF of the battery? Okay, so we see this is a series circuit and there's two resistors in series with each other. So we know the total resistance of the circuit. Remember, in series you just add the resistors together to get the equivalent resistance. So here you have a 10 and a 30 in series, so that would give you 40 ohms. You know how much current you have, 0.5 amps, so you can figure out the voltage of the battery then. So the EMF of the battery is equal to the current, 0.5, times the total resistance, so times 40, and that will give you the EMF. Okay. A little note here, it says the current through the 30 ohm resistor is 0.5. It's the same thing as through the 10 ohm resistor too, right? Because it's in series. Okay, and then again, if you want to review this section of the book, you can hit review and it'll go right to that section. Okay, so current times equivalent resistance gives you the voltage of the battery. All right, let's look at the next one. Okay, we have another series circuit, a 10 ohm and a 20 ohm resistor in series, connected to a 15-volt battery. What is the potential difference across the 10 ohm resistor? And then what's the potential difference across the 20 ohm? And then choose whichever graph corresponds to this setup as you go around the circuit. Okay, very good. So similar to the first one, but not exactly the same. In this one, we could actually figure out the current, right? Because we know the EMF of the battery, 15 volts. We know the total resistance. These are in series, one right after the next. Same current goes through them. So we have the total resistance, or in other words, equivalent resistance. We can figure out the total current. And then if we know how much current we have, using Ohm's law, we'll be able to figure out the voltage drop here across the 10 ohm, and also then the voltage drop here. Let's take a look at this. Okay, so here's the circuit. And then, again, it's the same current that's going through each element. Now, a 10 and a 20 ohm resistor in series rather. These are in series. The same current goes through each of them. We can replace that with a 30 ohm because you just add them together. So 15 volts, 30 ohms. Using this formula, the voltage of the battery is I times R equivalent. The current turns out to be voltage of the battery divided by R equivalent. So 15 over 30, or 0.5 amps. So why do I want to get that? If I know that, I can figure out the voltage across the 10 ohm. So the voltage across the 10 ohm would be the current times this 10 ohm resistor. And then the voltage drop across the 20 ohm would be the current times the 20 ohm resistor. So here we have 0.5 amps times 10 ohms, or 5 volts. For the other one, 0.5 amps times 20 ohms. This would be 10 volts. And then you see that they actually add up to 15, right? Here's minus the plus from the battery. That's doing something for us. Then we've got a voltage drop across the 10 ohm of 5 volts. And then across the 20 ohm, 10 volts. So if you go around the loop, this would add up to 0. 15, this is kind of the ski lift. 5 of it's being used there. And then 10 of it's being used here. Okay, so we actually did parts A and parts B. And then part C is, again, as you go around the circuit, 15 volts, the battery's doing something for you. Then you have a 5 volt drop across this one and a 10 volt drop across that one. So pick the corresponding picture that makes that work out. Okay, let's look at the next one. Okay, here's the next one. So if you're going to take the MCAT, going to medical school, something like that, I believe you take the MCAT. This is an MCAT type question. So let's see. Bioelectrical impedance analysis is a commercially available method used to estimate body fat percentage. The device applies a small potential between two parts of the patient's body and measures the current that flows through. with an estimate of the resistance individually of the muscle and fat between the 2 points, the composition of the tissue can be estimated. Okay, good. So basically, measuring the amount of current, you could estimate, the body fat composition. Assume that the muscle and fat tissues can be modeled as resistors in parallel. Okay, so parallel resistors. If the resistance of fat is 3 times that of muscle, what is the resistance of fat if 1 milliamp of current is measured when the potential difference of 0.5 volts is applied to the patient's arm? Okay, so we basically have 0.5 volts. These we could model the fat tissue and the muscle tissue as resistors in parallel. We want to know what is the resistance of the fat portion of this. Okay, let's take a look at it. This is not really a very easy problem. Okay, so this is how I've kind of modeled it. 1 milliamp comes in, splits off. This is the muscle side. This is the fat side. This resistance is 3 times as much. And these are in parallel with each other. And we know the voltage across here is 0.5 volts. Okay, so the question is, okay, this is R and this is 3R. We know more current is going to go this way through the muscle. Let me actually call this one I muscle. I muscle. More current's going to go through the muscle than it is through the fat side. So why do I need to know this? Well, I know that these are in parallel, so this is 0.5 volts. We don't know how much the resistance is, and we don't know how much this I fat is. But we do know this. 0.5 volts is equal to I fat times 3 times the resistance. Again, you can see the problem. We don't know how much this one is, and we don't know how much this is. We don't know how much that current is. We know the total amount of current, but we don't know how much of it goes this way. So we can't solve this uniquely yet. But we also know that 0.5 volts, this is in parallel also, so this is going to have to be equal to I muscle times R. So what I can do is figure out how much of the current is going to go here and how much of it's going to go here. Again, this is a perfectly good equation. I just can't solve for R or IF uniquely here. The other thing that I know, I'm going to put this here because this will help us, I fat plus I muscle is equal to 1 milliamp. Okay, so here's a little bit what I can do. The R's, I'm going to divide this equation by this equation, and the R's actually cancel out. And here it's 0.5 divided by 0.5. So this side becomes 1. The R's cancel out, so I've got 3 I fat over I muscle. So here's a relationship between these two things. I muscle is equal to 3 times I fat. So what do I need this for? I want to figure out how much I fat is. So I could use this back into this first equation and solve for it. So I muscle turns out to be 3 times as big as I fat, which makes sense too because the resistance is 1/3 as much. It's a lot easier problem if this is R and this is R. Then we know half goes here and half goes here. But that's not the way this one is. This is 3 times as big. You might try to guess like, well, it's 3 times as much, but it turns out that's not quite true. Let's set it up and see. So I'm going to take this for I muscle and plug it in here. So I have I fat in this equation plus I muscle, but I muscle is 3 times I fat, and then that's 1 milliamp. So 4 I fat is equal to 1 milliamp. So I fat turns out to be 0.25 milliamps. So a quarter of it goes through this side. So that's a quarter of the total current. So this is 0.25 going this way, 0.75 going that way. Okay, and then once you have I fat, now we can figure out how much this resistance is, because we know, going back to this equation, 0.5 volts is equal to I fat, which is 0.25 milliamps, times 3R. See, 3R. And then the only thing I don't know is R. Okay, so I'll have to do a little bit of math here. 0.5 divided by 0.25 to the minus third amps, and then I still have this factor of 3 here, and that'll give me the resistance. Okay, let me use my calculator. 0.5 divided by this quantity, 3 times 0.25 to the minus third. Okay, so like 670 or so ohms. Okay. Actually, that's the value of R, and the resistance of the fat part is 3 times as much. So really, we're looking for 3R. So 3 times R then would be this times 3, 2,000. Okay. So 2,000 ohms is the resistance of the fat. The resistance of muscle is 670. Now, if this were on an MCAT, this is a lot of work to do on an MCAT because I don't even think you get to use a calculator. So, from experience, you could guess that this is going to be 0.25 milliamps here. So this is 3 times as much as that. So this current has to be 3 times as much as this current, and it turns out it is. This is 0.25 milliamps. This then has to be 0.75 milliamps. So the muscle current is 3 times as much as the fat current. Okay, so it doesn't work out like a third goes through one and 2/3 through the other. It works out as the ratio of 3 to 1, so 0.75 to 0.25. So if you did a lot of problems, you could come up with that. But then it's still not a very easy problem. You still have to do this part down here just in your head. Okay, very good. Let's see what other parts we have to this one. Okay, and then if the resistance of fat is 6 times as much, how much of the total current goes through the fat in terms of current through the muscle? So I just kind of said how that worked out, so I'll leave that part to you. And then if 5 volts is applied across the patient's arm, what is the potential drop across the patient's fat? So again, if we're modeling these in parallel, the voltages are the same. So if it's 5 volts across there, this has to be 5 volts. Because in parallel things are they have the same voltage. Okay, and then here, if the measured resistance is 690 and the resistance of fat is 3 times that of muscle, what is the resistance of muscle? Okay, so I'll leave, well, maybe we can set this one up. Here's the total equivalent resistance, 690. So if the equivalent resistance is 690 and the resistance of fat is 3 times that of muscle, what is the resistance of muscle? Okay, let's actually work this one out. This is kind of a fun problem too. Okay, so they're telling you the equivalent resistance is 690. So we know that 1 over the equivalent resistance is 1 over R fat plus 1 over R muscle. And they're also telling us that 3 times the muscle resistance is equal to the fat resistance. So this is how this is in parallel. This is how equivalent resistance works out in parallel. Okay, and then I can put this fact into here. So 1 over the equivalent resistance is 1 over 3R muscle, right, because of this relationship. I plugged it in there, plus 1 over R muscle. And then I'm just going to put this under over a common denominator. So 1 over 3R muscle plus 3 over 3R muscle. Remember, this was 1 over R muscle. Now it's 3 over 3R muscle. Turns out to be 1 plus 3 is 4, and then the denominator is 3R muscle. And they told you the equivalent resistance is 690. So then you invert it. So 690 comes to the top, 3R muscle comes to the top, 4 goes to the bottom. Let's see, did I goof that up? Yep, it looks like I did. This should be 3R muscle over 4. Okay, so then R muscle, so this says 3R muscle over 4. Let me rewrite it when I invert it. 3R muscle over 4. Okay, and then I can multiply both sides by 4, divide both sides by 3. see this okay. 4 times 690 divided by 3 would be equal to our muscle. So our muscle okay, so 690 times 4 divided by 3, 920. And then if you wanted to, you could take this, go back to the original equation and make sure it all works out. I'm pretty confident that that's okay though. All right, let's look at the next one. Okay, so we want to find out the equivalent resistance of these two situations, this one and this one. First thing to ask yourself, series or parallel, and you can see that series, it would be the same current going through each element. So I'll leave that to you to figure out the equivalent resistance of both of those because they're in series. It shouldn't take you more than a minute or so. Next one. Now these are all in parallel actually. These are in parallel, these are in parallel, these are in parallel. So if you've got resistors in parallel, think back how you find the equivalent resistance of a parallel branch. And if you forgot, just hit this review button here. Okay? So here we have 3 resistors in parallel, equivalent resistance of 15. 2 of the resistors have resistances of 40 and 60. What is the resistance of the third one? Okay, let me set this up and then you can solve for it. Okay, so we've got 2 of these resistors are known. There's 3 altogether. 2 of them we know. One is 40 and one is 60, and the equivalent resistance of this parallel arrangement is 15. So 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. The way I'm writing this is the exact same thing as this. So when you look in the book, it'll say this. 1 over R1, whoops, equals 2. 1 over R1 plus 1 over R2 plus 1 over R3 raised to the negative 1 power. What I have written here is the exact same thing. You just have to invert it later on, which is perfectly fine. I just like to do it like this. So the equivalent resistance is 15, so 1 over 15 is equal to 1 over 40 plus 1 over 60. All these are in ohms. I'm just not writing the ohms part. And then 1 over R3. Okay, so 1 over 15 minus 1 over 40 minus 1 over 60 is equal to 1 over R3. Okay, so what you can do is do this in your calculator if you want to. 1 divided by 15, that quantity, minus 1 divided by 40, minus 1 divided by 60, you'll get some number, and then you've got to take the inverse of it to get to R3. Okay, let's look at the next one. Okay, so the very next one, it's another series circuit. R1 and R2 are in series with each other. How much power is dissipated by the 12 ohm resistor? How much power is dissipated by the 15 ohm resistor? So I'll leave it to you to figure out the total current, right? We've done problems like that already today. So once you get the total current, we can solve for the power. So the power, if you remember from the previous chapter, lots of ways of writing the power. Let's take a look at it actually. Okay, so the power is I times V, and it's measured in watts, which is a joule per second. You can write this as I squared times R, or V squared over R. These will all give you the power. So in this problem, I recommend figuring out the total current, and then that's the same current that goes through each element, and then the power is I squared times R. So do I squared times R for the first resistor, I squared times R for the second resistor. Okay, let's look at the next one. Okay, so we want to figure out the equivalent resistance for this circuit. So this is a combination of both. It'll be series and parallel when we start breaking it down. Let's actually go through this one. Okay, so here's what it looks like. We're measuring the resistance of this whole arrangement. So if you look at this, if current were to come in here at A, it would split off. Some would go this way, some would go this way. And then once it comes here, again it splits off. Some goes through the 30, some goes through the 45, and it comes back together, and this comes back together. So this branch over here is in parallel with everything over here. So let's try to, work this out in steps and see what we can come up with. So the 30 and the 45 are in parallel with each other. we can figure out an equivalent resistance for the 30 and the 45. So this is going to take a couple of steps. Now a 30 and a 45 in parallel, we can figure out that equivalent resistance. So between these two, 1 over 30 plus 1 over 45 is 1 over the equivalent resistance for that group there. Okay, you can use your calculator to do this. I'm going to say that this is 3 over 90 plus 2 over 90. That's the equivalent resistance just for the 30 and the 45. So I would have 5 over 90 is equal to the equivalent resistance, and then invert it. Equivalent resistance for that group would be 90 over 5. So let's see, that would be about, let me just do with my calculator. 90 divided by 5, less than 20, right? 18, yeah. So 18 ohms. So you can take the 30 and the 45 and replace it with an 18. So let's actually do that. So we still have a 42. Right, that's this part I'm drawing. These are all in ohms. Now you can take the 30 and the 45 and replace it with an 18. And then over on this branch, I have a 40. And this is back to being A. So I reduce this to this. And now you know this, there's a 42 and an 18 in series. So to replace the 42 and the 18 in series, you can just add them together. So 42 plus 18 will give you 60. And then here's point B again. And then you got 40 over here. So I'm, taking this circuit and making it into this circuit. Then you have a 60 and a 40 in parallel. So I'll let you work that part out. A 60 and a 40 in parallel. We're down to the last step to figure out the equivalent resistance of a 60 and a 40 ohm in parallel. Okay, let's look at the next one. Okay, so here's a circuit. It's a more complex circuit. It's not just purely series or purely parallel. So you've got a 12 volt battery, and then you've got a 20 and a 30 ohm resistor. These are both in parallel with each other, and then this combination is in series with this 12 ohm. We want to figure out the current through the 12 ohm resistor. Okay, so that's the actual total current of the circuit, right? Because whatever comes out of the battery goes through the 12, all of the current goes through the 12 ohm. Then it splits off. Some goes through the 20, some goes through the 30, and then it comes back to the battery again. Okay, so we want to know the current through the 12 ohm, the potential difference across the 12 ohm, okay, the current through the 20 ohm resistor, and then the potential difference across the 20 ohm. Oh, so we want to know this for all the different parts. So let me get us set up here. So let's begin by making this into a so-called simple circuit. So again, this is the total current that comes out of the battery. It splits off. Maybe I'll call this one I-20 and this one I-30. So the total current is equal to I-20 plus I-30. That's the first thing that we know. Okay, so once again, make this into a simple circuit. So a 20 and a 30 in parallel. Let me replace that by one resistor. So I'm just going to look at these two. They're in parallel with each other. So let me find the equivalent resistance of that. 1 over 20, and then this everything's in ohms here. 1 over 30. So 60 would be a common denominator, or if you want, just put it in your calculator. 1 divided by 20 plus 1 divided by 30, and then take the inverse of that. Okay, so this would be 3 over 60 plus 2 over 60, 5 over 60, and then I've got to take the inverse of that. So flip it upside down, 60 over 5, or 12 ohms. So the 20 and the 30, I could replace that with a 12 ohm resistor. So this circuit is being made smaller, making it into a simple circuit. So we've got 12 ohms, another 12 ohms. That's what this one is. And we've got 12 volts. Okay, so then this circuit, a 12 and a 12 in series. In series, you just add them together. And then finally, we have a so-called simple circuit. 12 volts, 24 ohms. We can get the current, squiggly E, divided by the equivalent resistance. So 12 volts, 24 ohms, 0.5 amps. So this is 0.5 amps, this is 0.5 amps, this is 0.5 amps. Right? They're all the same. They're equivalent circuits. Okay? So that's the current that goes through the 12 ohm resistor. That's the current that goes through here, through here. So if you want to figure out the voltage, so basically this is the first part, the current through the 12 ohm resistor. What's the voltage drop across the 12 ohm resistor? Okay, we can use Ohm's law there. Voltage across the 12 ohm resistor here would be the current times 12 ohms. So 6 volts. Okay, so that's what this is, 6 volts. If this is 12 and this is 6, this parallel branch here, if you were to measure it, would also be 6 volts. So the voltage across this is 12, but that's equivalent to this. So this is 12 volts, or sorry, 6 volts. 6 volts. So this is 6 volts, and this is 6 volts. So if you know this voltage drop is 6, you know how much the resistance is here. You could use Ohm's law to figure out how much this current is, and then same thing, you could use Ohm's law to figure out how much this current is. Okay, very good. So there's several parts to this one. You're off to a good start with this one. We got 3 different equivalent ways of looking at it, and we know the total current, we know the voltage across this, and we know the voltage across the parallel branch here. So you should be able to figure out these currents then. Okay, let's look at the next one. Okay, so same idea here as the previous problem. This is a more complex circuit, and there's a video tutor solution here, so you can take a look at the author working this one out. But what I would do is make this into a simple circuit. So you got a 5 and a 5 and a 5. These are all in parallel with each other. Replace that by one resistor, and then you can get the total or equivalent resistance of the complete circuit. Get the total current coming out of the battery. Luckily in this one, it splits off in 3 ways. B, C, and D. But these resistances are all the same, so you're going to have the same amount going here and here and here. So 1/3 of the total current will go here, and then 1/3 will go here, and 1/3 will go here. Okay. Excellent. So I'll leave that one to you to complete too. Lots of different parts here as well, but this one's actually slightly easier than the previous one. Okay, let's look at the next question. 1 microfarad, 13 microfarad, and 20 microfarad are connected in parallel. What is the equivalent capacitance? So I don't want to say too much, but review how capacitances add together. In parallel, it's kind of like series resistors. Okay, so capacitors in parallel are actually easier to add together than capacitors in series. But you can take a look here. Okay, next one. Okay, these are all connected in series. So in series, you add them together like you would add together parallel capacitors. So this would be, the equivalent capacitance would be 1/8 microfarads plus 1/10 microfarads plus 1/19 microfarads. And you can take a look back through this section here to review that. And then finally, here's a circuit. We can take a look at this. The switch in figure 1 has been in position A for a long time. That means the capacitor has been charged up. What is the charge on the capacitor immediately after the switch is changed? So we're going to take the switch, move it from position A over to position B. Okay, so if the capacitor is fully charged, it's charged up to 9 volts. You know its capacitance, 2 microfarads from the picture. You can figure out the initial amount of charge. Okay, think back to what we did initially with capacitors. Okay, so we'll get the initial amount of charge, and then we want to know what is the current through the resistor immediately after the switch is changed. Okay, so the capacitor is charged up to 9 volts. When you move the switch from position A to position B, that's when the capacitor could discharge. So we start at 9 volts, and then it's going to discharge through a 50 ohm resistor. You could figure out the initial amount of current. And then remember, as the capacitor discharges, the amount of charge on the capacitor gets less, the voltage gets less, and then the current's going to get less. We just want to know the initial current. So the initial current's going to be 9 volts divided by 50 ohms, right? I divided by R will give you the initial current. Okay, so there's several other parts here. What is the charge on the capacitor after 70 microseconds? Okay, so let's actually click this and go to the section, RC circuits. This is a capacitor discharging. So you've got to be in the correct section for this. Okay, it's just taking a second to open here. Okay, so it opened up here. I want to go to the correct part of this. Whoops, I think I hit the wrong thing. Okay, let me go back. There we go. And then I've got to scroll down. Okay, so discharging a capacitor. Take a look through this if you don't remember it. I put it in the notes that I went over. So this is what it looks like. The current starts with its initial value, and because it discharges, the voltage on the capacitor gets less, so the current's going to get less. Not in a linear fashion, in this exponential decay way of looking at it. Okay, so if you remember from the notes, I had I and V, but I also wrote it in terms of Q. So you could have Q is equal to Q naught e to the minus t over RC as well. Okay, so that's another way of looking at it. Actually, I think in the notes I started with this equation, and then I showed you how you can get the charge in the PowerPoint that I went over. Okay, so review this section, see what you can come up with, but remember it's discharging. All the formulas are here in the section. Okay, back to the homework. So like for part C here, you would put in 70 microseconds for the time. So in the formula, T is equal to 70 times 10 to the minus 6th. And then you can figure out the charge. So again, the charge is equal to how much charge you started with, E to the minus T over RC. Same thing over here. You just saw the formula for the current. You know the initial current. The current you have at some time is equal to the initial current, which you got from a previous part, e to the minus t over RC, and again, this is the time that they're using. And then part E and F, it's the same idea, it's just they're changing the amount of time. Okay? Excellent. And they want this in microcoulombs, and this answer in milliamps.